Hello, good evening, all. We'll start the week two session now.
Good evening, ma'am.
Yeah, good evening. Okay.
Ma'am, the yesterday's class is not recorded, is it?
Yeah, no, yesterday's class was recorded, but since we didn't do much, I didn't upload it. But did you get the sessions from previous class?
No, none of the.
Can you see on the portal if it is available?
It's not available in the portal nor updated in the calendar also.
Live session.
What happened in the yesterday's session?
Yesterday's session, not nothing much had happened. So that is why we are taking it today.
Ma'am, because it is clashing with
We also
PDSA. Most of
we
the students.
also had we also had a PDSA session at that time.
Yeah, that's what it is.
Today, right? Today you have the PDS session.
No, no, yesterday. Yesterday it was clashing. That's why most of the guys are out.
Oh, yesterday it was clashing with PDSA. I mean, this at the same timing, 8 to 10.
Yes, it is every week it is clashing. We requested a PDSA and now we thought of really making a request to you so that you can work it out not to have a clash.
Okay. I didn't know that. Thursday, you're saying Thursday 8 p.m. There is a clash with PDSA.
No, yesterday,
Friday. I mean,
yesterday was, yeah,
no, no. Is it clashing
Yeah,
today or
Thursday it
tomorrow?
is clashed, not
yes,
Friday. No, no, on Thursday.
yesterday. No,
That was Thursday.
Yeah, Thursday is clashing, right?
yeah, it was clashing. It's only there was
PDSA.
only an offset of 30 minutes.
Okay. Um. Okay. Okay. No, I was not aware of it. So if it is clashing, we can figure it out if we can move our session a little here there.
Yeah, yeah, yeah. Please,
Yeah,
thank you, thank
yeah,
you.
sure. Thank you. Okay,
Which
so
session is clashing?
PDSA. So I am not many of you will have PDSA, but some of you might have.
Yeah. Yeah.
Okay, so I will skip at least the initial part because it's just continuity and differentiability definitions. So I'll start from the linear approximation. Okay. Okay.
This presentation is available somewhere else as well, within the portal or something.
Not right now, but it will be available.
Okay, thank you.
Yeah. Okay. Submit. Let's see hand raise. Yeah, I zoomed it. Okay.
Ma'am, I
All
am
right.
also having a doubt in practice assignment.
We'll take it once the slides are done. Okay. So we'll start from linear approximation. So it is from lecture 3. We lecture 1, lecture 2 is like so in lecture 1 we have looked at some basic sets notations and sets limit continuity. So I'm sure you would have seen it already in maths too. So I'm skipping that part. Um, so let's go from start from linear approximation. So what we are saying is, let's say we have a function from R to R, some differentiable function. Okay, so it is differentiable, and if it is differentiable, what we can do is we can write f dash at f dash of x star. Let's say I'm saying f is a function which is differentiable at some point x equal x star. Okay, so what can you write this to be? We can write f dash of x star to be limit x tending to x star f of x minus f of x star divided by x minus x star, right? This is what we can write f dash of x star to be. Now, what we are saying is, I mean, uh, this is as x approaches to x star, but around what we're saying is if x is somewhere around approximately equal to x star, so assume that your x is approximately equal to x star, then in that case we can easily write f dash of x star to be approximately equal to this f of x minus f of x star divided by x minus x star, and this will turn out to be your f of x is approximately equal to uh, f of x star plus f dash of times x minus x star. So this is called the linear approximation. This f of x star plus f dash of x star, this is f dash, times x minus x star. So this is called the linear approximation of the function f x around the point x star, right? So this will be more like if you have let's say some function. So if I'm taking this point, if I want the approximation around this point x star, so this will be like, let's say this is the linear approximation. This is lx star of, sorry, lf of x star. Okay, so around this point x equal x star, I mean both these I mean they are very close, I mean these values are almost same, right? So this is a good approximation. I mean, whenever we want to approximate the function, this is what we do for this. But as we go higher and higher, the approximation definitely improves. But linear approximation is easier to work with. So in many cases, we just stick to the linear approximation. Now, yeah, so what we said, this L of LFX of x star, this is the approximation. This is the approximation of fx around x star. So this was linear approximation. If we have to take the higher order approximation, okay, is there? Okay. Now you are able, I mean, now it is properly zoomed in, right? I mean, not small.
Yes, ma'am, it is fine.
Okay. So what we are saying, what we are also saying is that this linear approximation of the function at a particular point, uh, someone, can you mute yourself, Subramaniam Mohan? Yeah, okay, thank you. Okay, so what we're saying is this linear approximation of the function at a point A is given by this, right? And this is indeed also the equation of the tangent line. So when you look at the equation of tangent line, this is how it looks like, right? This y minus y1 equal m times x minus x1. So this equation, the tangent line equation, and your this is very similar, right? So this is also the equation of tangent line. Now, okay. Now this was the linear approximation, but when we go to higher order approximation, we can also do like quadratic approximation. We can do a cubic approximation and so on. So what we do is we just take, so our linear approximation was f of x approximately equal to f of x star plus f dash of x star x minus x star, right? But when we do the quadratic approximation, you just add one more term for this. So you will have f of x star plus f dash of x star x minus x factor, x minus x star plus f double dash of x star by 2 factorial x minus x star square. Yes, it is the Taylor approximation. Okay, like in some cases, the higher order approximation, the quadratic approximation or cubic approximation are better than the linear one. But generally, we do not go for the higher order approximation because of its complexity. Okay.
Ma'am, f
Yeah.
of x is equal to the right hand side is for the approximation, is it? But the right hand side looks
Yeah.
to be more complex than the left hand side. So my understanding of approximation is to make it simple.
Yeah, yeah. I mean, so uh, like if your function was, let's say, let's take the example. Let's take, okay, so for example, let's take something. Okay. Suppose your f of x is 1 plus x to the power r, right? And I want to approximate this function around x star equal 0. Okay. So how will the linear approximation look like? It will be just 1 plus rx, right? So also, if you have looked at the lectures, I mean, it's quite easy to find out few values if you use the approximation. Let's say I had to find very complicated or very big. Here, let's say R is quite big, and I have to find some very complicated uh, value for effects, complicated value. Then in that case, if I could approximate, it's much easier to calculate, to work with. So even functions like log function, then exponential, these approximation are much like easier to work with. Okay. So okay, this was quadratic approximation, but when we have to go to cubic approximation, what will happen? So you just add one more term over here, and that will be f triple dash of x star divided by 3 factorial x minus x star whole cube. So you just keep on adding terms depending on how much approximation you want. Okay. Now, okay. Okay, I'll also just add one more. So yesterday we did not do the product rule, but we did the chain rule yesterday. So let's do the product rule also. Like we all know, like if we have a function which is a product of two different function, how to take the derivative. We all know, but just to see how we can obtain it from linear approximation. So this is the application of linear approximation. So you have the product rule. So let's say if you have a function which you can write it in the form of g of x, h of x, okay? And suppose you are interested in finding the derivative of f. So we know we know from formula that it is just okay. We know from the formula that this is just equal to gx times hx plus hx times g dash of x, right? This is what the derivative is. But how do we get this using the linear approximation? So what we do, what we'll do is let's try to approximate this fx. So approximate fx around x star equals 0. Okay. So in place of gx hx, what we will do is we'll write the linear approximation of gx and hx around the point x equals 0, x star equals 0. So f of x will become, what can we write gx as? We can write this as g of 0 plus g dash of 0, right, times x minus 0, right? And hx similarly, we can write it as h of 0 plus h dash of 0 times x minus 0 again, right? And this is what? This is going to be g of 0, h of 0 plus g of 0, h dash of 0 times x yeah, plus g dash of 0, h of 0 times x plus g dash of 0, h dash of 0, x square. Okay. So now the second term, I mean not the second term, the last term, you see this, there is a quadratic term. But since we just want to stick to linear approximation, so I will just ignore this quadratic term over here. So just ignore this. And we will have just g of 0, h of 0 plus x times g of 0, h dash of 0 plus g dash of 0, h of 0, right? So now if I compare this, the right hand side, if I compare this right hand side with the left hand side, so left hand side would be approximation of fx around x star equals 0. So that would be f of 0 plus f dash of 0 x, right? So comparing this, what we got is f0 should be equal to z0 h0, and f dash of 0 is going to be g of 0, h dash of 0 plus g dash of 0, h of 0, which is exactly same as what we knew earlier, right? So this is just using the linear approximation. We saw how we can find the derivative of a function if it is a product of two functions. Chain rule derivation we had looked yesterday, but maybe we can just do a small part of it.
Excuse me, madam.
Yeah,
Where does this last step?
the last step.
You said ignore, right? You should ignore that.
Ignore the last term because you have the quadratic term over here, x square. We don't want it. We just want to see the linear terms. So you can ignore that part.
Again, madam, that g of 0 and h of 0 equal to f of 0, how you are getting?
Okay, let me write over here. So what we did is we got f of x to be approximately equal to g of 0, h of 0 plus x time g of 0, h dash of 0 plus g dash of 0, h of 0, right? This is what we got. Now you approximate your fx around x equal 0. So what do you get from here? You get f of 0 plus f dash of 0 times x, right? I'm just comparing now. So this is the left hand side, this is the right hand side. If you compare these two, what do you get? You get, since your fx equal to gx times hx, your f of 0 now, I mean, it is quite clear that this should be g of 0, h of 0, right? And your f dash of 0
should be equal to that. Okay.
Yeah, should be equal to g of 0, h dash of 0 plus g dash of 0, h of 0. Okay. So this is same as what you would have done generally. Like if you had to find, if you had a function of two, if you have a function which is a product of two different functions, and you have to find the derivative, you do first times second derivative plus second times first derivative. Right? That's exactly the same thing that we obtained using linear approximation. Right?
Okay, madam.
Now,
Thank you.
now let's look at the chain rule. So this we had done yesterday, but let's quickly go through it. So now let's say your function f of x is equal to g of h of x. Okay. And we want to find, again our goal is to find f dash around x equals 0. So what we'll do is, first we approximate r h around x equals 0. So what do we get? We get f of x to be approximately equal to g of h of x. We can write now as what can we, this we can write it as h of 0 plus h dash of 0, x minus 0. So x minus 0, I'll just write x. Okay. So now this is after we approximated h of x around x equals 0, right? So now what we will do, now you have to do approximation for g. So you approximate g around h of 0. Okay. So when we do it, we'll get f of x to be approximately equal to g of h of 0, right? Plus it should be g dash of h of 0 times x minus h of 0, right? So in this case, our x is h of 0 plus x h dash of 0 minus h of 0. Okay. So this turns out to be g of h of 0 plus g dash of h of 0 times x of h dash of 0. Okay. So now again you compare, so initially your fx was g of h of x, right? So again we do the same thing, we approximate our fx around x equals 0. So we get f of 0 plus x time f dash of 0. Again, just looking at both these, comparing the right hand side and the left hand side, we can see that our f of 0 is g of h of 0, and our f dash of 0 should be g dash of h of 0 times h dash of 0. So this is what we do in general also, right? We take the derivative, and then whatever the other function you have, you take the derivative again. So this is the chain rule, and this we obtain using the linear approximation.
Ma'am, I didn't understand this. How did you replace x with g h of 0 plus x into h dash of 0?
Yeah, because now you have in place of x you have h of 0 x times h dash of 0, right? And generally what do you write? You write g of, let's say if you have if you have to approximate g of x, so around some point x star. So what you
Yeah.
will do? You will do g of x star plus
Plus
g
g
dash
dash of
of x
x
star
star
times
into x
x minus
minus
x
x
star.
star. Yes.
So now our x star is h of 0, okay?
Okay.
So g dash of h of 0, g of h of 0, which is this, g dash
Yeah.
of h of 0, which is this, and then x
Correct.
minus x star, which is x. Now x in this case is h of 0 plus x times h dash of 0.
Okay.
That this is x, and minus x star, this is x star.
Okay.
Ma'am, why do you call it a chain rule? Where is the chain action is happening?
It's here, no? I mean, this is what we do. This is what the chain rule looks like in differentiation. I mean, let's say you have to differentiate. Let's say you want to differentiate log of, I don't know, let's take e to the power 2x, right? So your first function, so if you differentiate, what do? You first differentiate e to the power 2x, which is just e to the power 2x, and then you differentiate this, which will be 2. This is exactly the same thing, no? This is the chain rule. What we just did, this is called chain rule.
Basically, composite functions.
Composite function, yeah.
So now we are like deriving the chain rule using linear approximation.
Using linear approximation, yes. So as we did yesterday, I mean, the approximation can be around any other point. It shouldn't be just 0. So yesterday we had solved one problem where it is around x equal 1, right? Okay. So now we had also maxima, minima, and saddle point. So you know that um, you know the conditions for that, right?
Only if
Maximum, minimum, saddle point, and all those things, huh?
Yeah.
Ma'am, if you can like discuss in like 3-4 minutes, if we can just cover.
Yeah. I see
Yeah.
some chat in the some questions in the chat box. This is about discourse, is it?
Yeah.
Yeah.
So discourse is not accessible.
It is accessible, madam.
Okay, so is it not accessible for some people?
You're referring, ma'am?
Uh, no, I'm just asking the some Prince.
Maybe that Prince Murari would have not been able to access. Maybe he has written, madam.
Okay.
You can continue, madam.
Okay. All right. So this was about linear approximation, and then when do you say like how do you find the maximum, minima, and saddle point? So if you take the derivative f dash of x and you substitute it to 0, right? So the point at which the derivative is 0, either it turns out to be maxima, minima, or saddle point. So what are the conditions for maxima, minima, or saddle point?
If it is negative,
It is negative, it is maxima.
Maximum.
If the second derivative is negative,
saddle point.
so I mean, you find your point x, you find the critical point first. You find the critical points, and what do you mean by critical point? The points where such points where your derivative is 0. Okay, the points where derivatives are 0, those points are critical points. You find the critical points, and then then you check for double derivative, right? So if double derivative turns out to be less than
Double
0,
derivative at those critical points, right?
yes, then it is maxima. If it is less than 0, sorry, I have taken less than 0. If it is greater than 0,
Minima.
then it is minima. And if it is equal to 0,
Saddle.
it's saddle point.
Madam, do we have examples to understand this better?
Madam, this is only for one variable, correct, no, madam? There is one
This
more.
is only one variable. I mean, I don't think we have seen this in, I mean, not in this week. We have not seen anything else.
Multivariable.
Yeah, you will come across it when you go to, I guess, week 7. So week 7, there is all of this was higher order.
Yeah. Because max to end of last, we have studied all these things, no? In multivariate also.
Yeah,
Okay. For
We
this
have
week,
studied
only
all
for
of
single
this.
variable.
yeah.
Okay, madam.
This is just for single variable.
Madam, do we have questions to understand this better? How do we solve these things?
Oh, questions, maybe not today, but the sessions we'll do tomorrow for problem solving, there we can do. But there are definitely some problems. Let's see if there is time at the end we can do.
Please.
Okay. So now we come to line. Yeah, now we come to lines, right? So how do you find the equation of line? To write down an equation of line, what do we need? So first thing is through which point the line is passing. But is that sufficient? No, right? Because if I give you a 1 point, I mean, there can be many line that passes to this point. But to specify which line we want, you need one more component. And what is this component? This component is direction, right? So the other component is direction. So whenever we have to find the equation of line, so you need two things. The first thing is the point through which line is passing. And the second is direction, in which direction you want, right? So it's like if you take, let's say, equation of line that passes, let's say that passes through the vector u in along the direction v. Okay. So what can we write this as? This will be some x minus u
X is equal to u plus alpha v.
equal alpha times v. So this will turn out to be x equal u plus alpha v. Let's put this, right? So this is the equation of line which is passing through a point u and is in the direction along v, right? Now, okay. Now the second question is, what if you are given, you are given 2 points. Let's say you have u and you have u dash. Okay. So if you have 2 points given and you have to find the equation of line, then how can you do this? So again we do the same thing. So what will happen is your x, now let's say that your line is passing through u, so x minus u, and is along the direction x minus u um, along the direction u dash minus u, right? So my direction now is u dash minus u, and what we are saying is the line, the line you see here, this passes through u. Okay, so we can write this as x minus u equal to some alpha times u dash minus u. Yes, Sarfaraj.
Then is this we are assuming that it is passing along the direction u dash minus u?
I mean, you can also, I mean, if I give you just 2 points, how do you find the equation of line?
We
See,
will
Slope in the
first
sixth
find the
form.
slope. Yeah,
go ahead.
I'm saying we will find out the slope of that line and then we will apply it in the equation y minus y1 is equal to slope into x minus x1 like that.
See, to define the equation of line, you just need through what point the line is passing, and you need just one direction, right? These are the only two things you
Yeah,
need.
okay.
So I have now two cases. I mean, you can have two cases. One is either a line is passing through, first is when line is passing through u and is along, and the direction what I'm fixing is u dash minus u is the direction. Okay. So x minus,
Then, but this is I am not getting u dash minus u. What is this?
this is the direction. I mean, here the direction was specified, no? I
Is it a
mean,
vector?
it is a vector. Yes, it is a vector.
Okay, okay, okay.
Yeah. So, okay. So I can write x minus u equal alpha times u dash minus u. And this can be written as x equal u plus alpha u dash
Then can we
minus
reverse this
alpha.
also?
Yeah, you can do. I mean, you can write u minus u dash. No issues.
If we say like we have a point u dash and it is in the direction of u minus u dash, right?
Yeah, that I will write that form also.
Okay.
Okay. So this is x equal, what can we write? We can write x equal alpha time u dash plus 1 minus alpha time u, right? This is what we can write. And what is this? This is equation of line, which is passing through u along u dash minus u, right? Now let's say I want the equation of line which is passing through u dash, so x minus u dash, and is along the direction u dash minus u. So this you can write it as x equal u dash plus alpha u dash minus alpha u, and this is equal to 1 plus alpha u dash minus alpha u. Maybe you would have seen this in some different form in the lecture, but all are same, right? So this is just equation of line passing through u dash along u dash minus u. Yeah. Okay.
Madam, the difference between the two lines is it is
No,
opposite
both
direction.
both are the same line. It's a different way of writing.
And direction, there will be two direction. I mean, any number of directions. Direction also is same.
Direction is both are the same direction, no?
Uh,
Okay.
Is the direction u minus u dash or u dash minus u?
You can take anything. That is not
Okay.
a problem.
Okay. Vector will have both directions. The line, both are same only. Equation of line will be same.
Yeah, yeah,
Okay. Thank you, ma'am.
yeah. Okay. So next,
And madam, u and u dash are the 2 points, or
2 points. Yeah, 2 points.
and we're denoting direction as mu dash minus mu, right?
Yeah.
And x is another point on the same line.
Yeah. I mean, to write the equation of line, you need some. I mean, you need some variable, no? Okay. So there is also something called hyperplane. So there is not much has been discussed there. So I'll just write it down. So how does the equation of hyperplane looks like? It is just a vector which is like normal to. Wait, you can write this as. The equation of hyperplane W transpose X equal B. That is what you have seen, right?
Yes, ma'am.
Yeah. So
You're writing something because that's not visible at all.
I am writing. So hyperplane normal to any vector W. So let's say this is a normal vector W with value B, we are saying, right? So to find out like how do you write the equation hyperplane? So it is set of all x such that W transpose X equal B, right? So set of all x belonging to Rd, if you're talking about D dimension, such that W transpose X equal B, right? So now this is more like if you take any two vector on this plane, right? So let's say X and A. So this X minus A should be perpendicular to this W vector, right? So if I'm saying, when do we say two vectors are perpendicular? If they're if A transpose, we say A is perpendicular to B if A transpose B equals 0, right? So same in this case, we can say W transpose X minus A should be 0, right? So this will turn out to be W transpose X minus W transpose A equals 0. So if when we are saying a hyperplane normal to the vector W with value B, right? We are saying B is the value. So this B is nothing but this W transpose A. So you get W transpose X equal B. So set of all such X which is belonging to Rd such that your W transpose X equal B. So this is equation of hyperplane.
Ma'am, just a small doubt. B is actually the offset value, right? That is the
Offset value, yeah.
distance between the plane and the plane and the point X, or what is
No,
B?
no. B is W. Okay. So this is the plane I'm talking about, right? W is some vector which is perpendicular to this plane. Okay. And And to define this plane, I need some two vectors, right? So let's say my one vector is x and I have another vector as a. So this x minus a, if I take, so because this x and a are on this plane, if I take x minus a, so that should be perpendicular to w, right?
Yeah.
So, and when do I say two vectors are perpendicular? So two vectors are perpendicular when a transpose b equals 0. So I have just done w transpose x minus a equals 0, and from there we got w transpose x equal w transpose a, and this w transpose a is what I am writing as b.
So it's just some constant. Does it
Yeah,
have any? Okay.
yeah. So this is a question of hyperplane, and it always lies in like, let's say it always lies in d minus 1 dimension. So if your vector space is in Rd, uh, if your space is Rd, then hyperplane will always be one dimension lesser than the vector space. Right? So it will be in d minus 1 dimension. Maybe all these things you will study later when you go to MLT. So just take questions, and the formula is what you need to know right now. Okay. Then we have partial derivative. Let's go to the slides now. Okay. So in partial derivative, so when we are saying fx or fy, so fx is what, when we say fx, it is just rate of change of x with respect to x. So how the I mean how your function is changing when you're just, I mean, keeping your y constant and varying your varying your f over x. If you want to look from the figure, maybe, let's see. Okay, wait. Let me just. So let's say this is some surface, some paraboloid. Okay, this is, let's say, z axis. Let's say this is y axis. This is x axis. Okay. Now, if I'm talking about f of x, it means um, I'm keeping my y constant and varying only over x. So let's fix some y over here. So if I fix some y, so then your x will vary, right? How do I draw this? Okay. Wait. Yeah, let's fix some y naught. So let's say this is my y naught, and your x is varying, right? So your x is varying. Okay. So this will look like something. Maybe you can use GeoGebra and something to see this. So like you are just intersecting the surface with some plane. Okay. So when you intersect the surface with some plane, this is how it will look like. So you will get a curve on this surface, right? And the slope of this will be your f of this partial f of x. And same thing if you have to do for f of y. Uh, in f of y, you're just fixing your x and varying over y, right? and that slope of the tangent line will give you the derivative. So this is just a geometrical interpretation. Same thing. Maybe the figure here it's not very clear, but you can try it using GeoGebra or something. That gives a better visualization.
The first that you showed was the constant y.
I mean, this is like this is a, let's say, some surface, right? And this is some surface, and uh, now you're fixing your y, right? You're fixing your y and varying over x. So you can see that I have fixed my y. So this is my y naught, and I'm varying over x. So this will give me a curve, and this curve is what? This curve you can call it as
F of x.
f of x comma y naught, because y naught is fixed.
Okay.
Yeah, and if you take the tangent on this, then that slope of that will give you the derivative. Yeah. Okay. So similarly, when we write f of y, it is just rate of change, a rate of change of y with respect to rate of change of f with respect to y when you keep your x constant. That is f of y. And these are like specific direction. Like when we talk about fx, we want to see the change in the direction x. When we talk about fy, we want to see the change of f in the direction y. But in general, if we want to see the rate of change, so in any given direction, then we have directional derivative that comes into the picture. So that will be like do the rate of, I mean, if you allow both x and y to change simultaneously in some direction, u. And how is this directional derivative given as? So let's say I want to see the rate of change of f in the direction u. So this is just this is given by just grad of f dot u, and u is some direction, right? U is any direction. So if I'm talking about function of two random variable, then my u would be u1 comma u2. And we generally takes this uh, direction to be of this vector u to be magnitude 1, because we are just interested in the direction, right? So any vector, if you want to see the rate of change in a particular direction, it's uh, we take we find the unit vector so that it just gives you the direction, right? So in many question you would have seen, in some question sometimes vector u is given as the unit vector, sometimes it is not given as unit vector. So in that case, you first make it to the unit vector and then find the direction derivative. Okay. And what is this gradient? So gradient is just the derivative. I mean, you have seen f dash. So this is only when your function is from real value to a real number to real number. But when you're defining a function from R2 to R now, so you need a vector in that case. So this grad of f, it's just the generalization of derivative in higher dimension, right? So grad of f just the derivative, it acts as derivative, just the generalization of derivative in higher dimension. Okay. So when we simplify this, so this would be dou f by dou x u1 plus dou f by dou x1 dou f by dou x2 u2. So this will be the directional derivative of f in the direction u1 u2. Okay. Yeah, this is what we have done here. Yeah, did we miss any part? Direction derivative after that.
Ma'am, you can consider partial derivatives as directional derivatives along the x-axis and
Yeah,
sorry, and
yeah, you can. So like well, fx was just like when you want to see the change in a particular direction x, but it is like a more generalized version, the directional derivative. Yeah.
yeah, yes, ma'am, yeah.
Okay. So that was all I had in the slides. If you have anything from the lecture or from questions, you can go ahead.
You said you might take up some
Problems.
problems to
Yeah.
solve.
Yeah. Just give me a minute. I will pick it up.
Like for the product rule or chain rule or linear approximations.
Ma'am, have you covered lecture 2.6?
I was on mute. No, I was asking 2.6 has directional derivative, right?
I haven't done it, ma'am. That's why I was asking.
Okay, okay.
Gradient is just this that dot product, the first part, right? The
Gradient is just, yeah, grad of f.
so like the partial derivatives on
Yeah,
different variables, we just put them together, and that is gradient.
yes. I will open the problems
Now, how
now.
do you remember stuff across terms?
Across terms, like terminologies or
Like the concepts, because like we have studied all of this, but it is not very fresh.
yeah, I think you just need to revise. I mean, if even I forget, but you need to keep revising and like
Okay.
they solve problems. So solving problems like help you remember things. Okay. Yes. Okay, in a tutorial there are quite a lot of problems, so I will take from there.
Ma'am, for like every subject, can we have like a list of questions like 20, 25, which in later terms we can just see if we can solve those questions, and then if we are able to solve those questions, we'll be also revising all the concepts. So maybe periodically we just take that list of questions and solve it.
Um, you mean from each week if we can have some question?
No, no, no. Okay,
No?
like it was. I can just solve the quiz questions. Sorry, I can just probably do that. Okay, thank you.
Yeah. Okay. Let me open it. Okay. Let's do this problem. So this is what we just discussed. So this is finding the directional derivative. You have to find the derivative of f in the direction of u at the point 2 comma minus 3. So what do we do? How do we solve it? So we know directional derivative of f over a point some x, right? In the direction u is just grad of f dot u, right? So first we need to find the grad of f. And what is grad of f? It is dou f by dou x and dou f by dou y, right? And what is dou f by dou x?
2x minus y.
Partial
X minus
derivatives.
y.
2x minus y. And what is dou f by dou y?
Minus x.
Minus
Minus
x.
x. Now you need to find the point is given to you, right? So you need to find this at the point 2 comma minus 3. So what this will become? 4 plus 3, which is 7, right?
7 minus 2.
Minus 2. Okay. Now you see this direction is not unit vector, right? This is not a unit vector. It is given as 0.6 comma 0.8. So we need to first bring it down to the unit vector.
This is a unit vector.
This is
It is a unit.
okay. This is 0.64 plus 0.36. Yeah. This is unit vector, right? Okay. Right. Now you take the grad of. You find the dot product of grad f dot u. So what you will get? So grad of f is 7 minus 2 and dot product with 0.6 comma 0.8, right?
2.6.
2.6. Yeah, so 2.6 is the directional derivative. Yeah, this is the right answer. Let's do. Okay, let's do this question. Can you try giving the answer for this? Derivative of fxy in the direction of 2 comma 1. So if you don't remember the derivatives for cos and sine, so cos of x just minus sine x.
It's 2 by root 5 cos y
2 by root 5
cos y
cos y
minus 1 by root 5 x sin y
minus 1 by root 5
x sin y.
Sin y.
x sin y. Okay, let's see. All of you are getting the same answer?
Yes, ma'am.
Okay.
Yes, ma'am.
So 2 by root 5 cos pi minus, yeah, that's right.
Then can you go to the previous?
Previous question.
Yeah. No. That we were getting the cos x. Yeah.
Yeah,
There is a
this,
solution for this.
yeah, there, here.
Okay.
Yeah. Okay. Okay, let's do this. So here you have a question where you have to find the linearization of fxy, which is defined as x times e to the power xy at the point 1 comma 0, and then use this linearization to approximate the function value at the point 1 comma 1 1.1 comma minus 0.1. So can you try this out? So you have I will just write the approximation. So f of xy this is approximately equal to f of x naught comma y naught plus grad f at the point, or let's write this as v, maybe some point v, plus grad f of v transpose x minus v. And here my v is x naught or x star comma y star, whatever you want to say it. Yeah, I think we didn't see, we only saw the linearization for function of one random variable.
Yes.
Yeah.
Nirvaman, can you show me the previous problem solution?
Sorry. Yeah, let's just look at what it should look like. So when you have function of two variables x and y, and you want to find its linear approximation in the neighborhood of some point a comma b, then it is given by f of ab plus dou f by dou x eb x minus a, dou f by dou y at point ab y minus b, and this is nothing but, so something, okay, when you had the function of one, when you have just one variable, then in that case your fx was approximately equal to f of x star plus f dash of x star x minus x star. Now since you are going to a higher now you have two variables, so this derivative will be replaced by gradient, so it will turn out to be, so let's say this is fx, now this is a vector, right? So this is approximately equal to some f of x star plus this derivative will be equivalent to the grad, so grad f of x star transpose x minus x star, right? So if I'm taking my x to be x comma y and my x star to be a comma b, then this will be f of a comma b plus grad f of a comma b transpose x is, again you have xy minus ab, right? And this can be written as this term, it is nothing but dou f, okay, this you can write it as dou f by dou x at the point ab times x minus a plus dou f by dou y at the point ab x minus y minus b, right? This is what it is.
Ma'am, shouldn't x and x star be column vectors?
Sorry, x and
X star be column vectors because we're taking the transpose, right?
This is column vector, no? I mean, I have written it as column vector.
Okay, okay, because you wrote it in a line. Okay, okay.
No, here I have written it like that, but this is how it is.
Yeah. Okay.
Yeah. So now can you use this and find the linear approximation of, so saying linearization is same as linear approximation. So find the linear approximation of fxy at the point 10. So this is the first question.
X plus Y.
X plus y. Okay.
Other one is
When I am getting X plus
1.
Other one is
value is
1.
value is 1. Okay. So all of you are getting the same answer.
Yes, ma'am. I also got the same
X,
answer.
Okay.
I got
let's-
x plus y minus 1 and the final answer minus 0.1.
Okay, let's see the answer. So first we need to find the derivative. So we do dou f by dou x at the point xy. So that will turn out to be this. So that is xy e to the power xy plus e to the power xy. So this is dou f by dou x. Now dou f by dou y, if you do, it is just xy e to the power xy. Sorry, x square e to the power xy, right? That is our dou y. So my first step is to find the gradient. Now gradient at the point 10, how will it, this will be, okay, let me go to the slide. Yeah. So at the point 10, my function value is just 1, right? And at the point 10, dou f by dou x and dou f by dou y is also coming out to be just 1. Okay. So if you find the linear approximation, it will be just x plus y. So yeah, x plus y is the right answer. And now we have to use this approximation to find the value of, we need to find the value of f of 1 comma 1. We needed to find f of 1.1 comma minus 0.1. And we had found out that this fxy is approximately equal to x plus y, right? So we can just do this to be 1 plus 1.1 minus 0.1, right? And that will turn out to be 1. Is it okay?
yes, ma'am.
Okay. Then you have okay. Now your question is f of x equal under root x plus 4. Now what should be the value of f of 6?
Will you save this PDF in the documents?
Yeah, I will share this document. This is actually the tutorial question, so you don't have to worry. These are just the tutorial questions that you have in your week 2.
Even if you can share this PDF, it will be great.
Sorry?
Even if you'll share this PDF, it will be great for me.
Okay, I can do that. 3.16. How did you find it?
I think it's not correct, but you just substitute it in the function, right? Is there?
Oh,
DDD x approximate root under 1 plus x. F6 is 10. We can DDD of approximate root under 1 plus x at x equal to 3.
can you repeat? Can you repeat?
So f6 is 10, so I can immediately approximate the function 1 plus x at x equal to 3.
X equal 3, you're saying?
No, x equal 5.
Yeah, x should be 5, no?
Because we know the value. This is actually when you substitute 6, it comes to root 10. And we know the value of root 9.
Root 9.
So
Yeah.
root 9 is 5 plus 4. So x is 5.
Yeah.
And approximate around 5.
Yes. So you do the linear approximation of fx equal x plus 4 around x equal 5. Right? So all of you did the same thing. You formed the linear approximation of f of x around x equal 5.
I got the equation, ma'am.
What is the equation?
I got it as 13 by 6 plus 1 by 6x.
13 by 6
plus 1 by 6x.
1 by 6x.
Yeah.
Okay.
Now what we do, we have to substitute x as 6, right?
Yeah.
So that will be 13 by 6 plus 1. So that is 2.13 by 6 is
It's going out to be 3.167.
2.16 plus 1. It comes
Yeah.
to 3.16.
Yeah. So yeah, this is yeah, that is right. So what we will do is, we have to find we have to find f of 6, right? And f of 6, you see, it will turn out to be root 10, but we already know like under root of 9 value, right? So what we can do is we can approximate our fx around the value x equal 5. Okay. So my fx is root x plus 4. Now if I have to find the linear approximation for this, it should be linear approximation of f over the point some, let's say, some x star. This would be f of 5 plus f dash of 5
into x minus
5, right? And my f of 5 is just under root
3.
of 9, which is 3. And f dash of 5 will be, so f dash is what? F dash is 1 by
2
root x plus 4.
Yeah. So if I take substitute 5, so this is 1 by
6
and x minus 5. This is the linear approximation of fx. So now if we have to find the f of 6, so f of 6 will be like approximately equal to L of this 5 f of intake 6, right? So this would be 3 plus
3 plus 1 by 6.
3 plus 1 by 6.
Yeah, 1 by 6, which will come out to be somewhere 3.16 something.
Yeah.
Okay. All right. Then we have also done the quadratic approximation. Okay, so the goal of this exercise was you find the linear approximation, you find the quadratic approximation, you find the cubic approximation, and see which gives you the more closer value. So if you have done the tutorials, you would have seen this. And which one gives the okay. So it's like almost all of it gives the same value over here. So the cubic is 3.1.
Linear gives 3.167, and I think the higher order gives 3.162, and that is the actual value of root 10, 3.162.
Okay, okay.
So that's how it is more approximate.
Okay. Oh, okay. Somebody is asking if we can do something else. I don't have anything else to present. So if you have any doubt, you can ask me.
Excuse me, ma'am.
Yeah, Anu.
Ma'am, yesterday you were explaining some inequality. I wasn't able to understand that. Can you do it again?
Okay. So yesterday we were doing Cauchy-Schwarz inequality, right? So go back. Yeah. That was a practice assignment question. I think some question number 14 maybe. I don't remember the number.
Yes, ma'am.
Question number 14 it was, I guess. So there, see, what is our Cauchy-Schwarz inequality? It says this is minus of norm of A, norm of B times norm of B is less than equal to is less than equal to A dot product of A with B is less than equal to norm of A.
Madam, A transpose B, no, madam.
I have written A dot product of AB.
Okay, okay.
Yeah. So let's write it as A transpose B. So the question was, if we take some B as a one vector as a scalar multiple of other. So if I take, let's say, B to be some C times A, where C is less than 0, okay, then the option was my option was A transpose B equal minus of norm of A, norm of B. I guess this was the option. Okay. So how do we prove this? So if I take LHS, so my LHS is A transpose B, okay? And what is So this is A transpose. And what is B? B, I can write it as sum C times A. And this will be, since C is just a constant, so we can pull C out. And this is C times A transpose A. And I can write this as C of norm of A square. Right? Now if I look at RHS, this is minus of norm of A, norm of B. Right? And what is norm of A? So okay, norm of A I can just write, and norm of B will be some C time norm of A. And using the property of norm, this norm of C of A would be modulus of C norm of A, and again you have norm of A, right? And since C is negative, C I have considered to be negative because this is what question says. So if C is negative, this will open as minus C. So minus C will turn out to be just C. And this is nothing but norm of A square. So you see this LHS is same as RHS, right? That is why this option was right. Is this okay?
Yes, ma'am.
Okay. Any other question?
Activity question, practice assignment question number 7.
Sorry, activity question?
7.
Uh,
Practice assignment. PA2 question.
PA question number 7. Okay, PA question number 7. The question is, which of the following is the best approximation?
Yes, ma'am. E to the power. We approach this like the previous question you solve. First, find the known value e to the power.
Okay, you have to find, this is question number 7. You have to approximate e to the power 0.00, what is that? E to the power 0.019. 0.019, right? This is the question. And you have to approximate, use a linear approximation around the point 0. So this you have to do around 0. So if you look at the function, this is more like f of x equal e to the power x, right? Now, if you find the linear approximation of e to the power x around the point 0, how does it look like? This will be L of f of x, right? Around the point 0. This is f of 0, so which is e to the power 0, plus f dash of 0, x minus 0. And what is f dash of 0? That will be just 1. So this is just 1 plus x, right? This is right, no? This is okay?
Yes, ma'am.
Yeah. And what is your x here? What is x? You want to approximate e to the power 0.019. And we have written the approximation for the function e to the power x. What is x here?
0.019.
0.019.
0.019. So this is approximately, so what we're saying is that my e to the power 0.019, this is approximately equal to 1.019, right? So this should be the answer.
Madam, how did you got this f dash 0 as well?
How did I get
F dash 0 as well.
f dash 0 as 1? Because f dash of x is what? F dash of x equal e to the power x. And f dash of, when you take x to be 0, this is just 1.
Okay.
Okay, any other question? Amit, do you have any question? Yeah, raise your hand.
No, ma'am, no, thank you.
Okay.
Actually, your the PDF is going to be much handy, but
Sorry, your?
this PDF will be much handy for
Aha, okay. I will share this. I will share this PDF. Yeah. Anything else anyone has?
Ma'am, are these sessions recorded?
This is live streamed.
So those won't be recorded.
Yeah, it is not recorded. It is live streaming.
Okay,
Maybe I'll put
But it automatically gets recorded as well, right?
No, it doesn't get recorded.
Okay, because I didn't find any YouTube link of previous session. I missed to attend that. So I just
Okay.
wanted to know.
Maybe I'll put the link. I'll put the links in the calendar.
Sure.
So yesterday's one was recorded.
Yesterday one was recorded, but since we did not do anything much, so I didn't upload it.
We had,
So
we had a
today's
1
one-
hour session, something like that, right?
Yeah, but nothing much has been done. So whatever we had discussed yesterday, today also we have discussed it. So it's okay.
Oh, is it?
So this today's session will be uploaded, right?
Yeah, I mean somebody has already pasted the link. You can take it from there.
So today's session is not recorded. Then how do you upload it?
No, it's like if it's live streamed, it is automatically getting recorded. If for some reason it is not being live streamed, it will be recorded and uploaded later.
Yeah, exactly.
Okay. Thank you.
And ma'am, can you please take care of the clashing PDSA and
This is every week, right? You're
Every
saying
week.
Thursday. Yeah, I will check.
right? Thank you.
Can we not have it later half of the day, madam, instead of 4 to 6? Is it possible to take it a little late?
But again, many people will have some session, right? Because yesterday I had checked and scheduled it for 4 because some.
Which
some of
session?
you-
Which session are you talking about?
Today's session. I mean, today's session that we took at 4 o'clock.
No,
So-
yesterday's session only
But
clashing.
like this session is only because like you were not feeling well, so you.
Yeah, that is why I had kept
This
it
is like
today.
an aberration. This
Then
usually
going
doesn't
forward,
happen.
it will be a 4 to 6 only, or we're going to change the time?
No, this was an extra session because I didn't take yesterday's session, so that's why it was scheduled for today. But in general, if you're saying Thursday session are clashing, we'll check that and we'll see if something can be changed.
Ma'am,
Yeah,
you
because
can
tomorrow,
do this time.
again,
no?
tomorrow session again is 4 to 6, right?
Saturday will be 4 to 6.
Okay.
Yeah.
I'm
Today
thinking
also can we make it regular 4 to 6 so that it can be avoid clashing on the PDSA?
Sorry.
Today also, if you make it 4 to 6 all the weeks, then clashing with PDSA is just taking care.
But
We
to
do-
4 to 6, not many people may join. That's why we don't keep it generally 4 to 6.
Subramanian, people may have their normal office, no?
Yeah,
Got
this
it?
was like an extra session. That is why we kept it. But
Yeah,
many people may not be free at 4 o'clock.
5 o'clock?
That is also difficult.
because people are like working, right? Like,
That's 6
I'm
o'clock
not working,
PDSA
but
is starting.
others-
No, Subramanian sir, you're very correct, sir. It's just that many of us are only get free by 7ish in the evening, normally.
Well, that's all taken care, taken by different subjects.
I appreciate that, but it's just that generalizing a time may be a little difficult.
Okay, let me say